happy to introduce our speaker today, Professor Jon Sievers. Jon did his PhD at Caltech, then did a postdoc in CETA here in Princeton, and then became a faculty at in South Africa at the University of KwaZulu-Natal, and then moved to McGill, where he is now. He's an expert in measurements of the cosmic microwave background, in studying galaxy clusters, in particular with the Siemens-Ludwig effect. And he'll tell us today about measurements of the redshifted 21 centimeter line from the distance.
Thank you very much. Okay, so if you have any questions about the other things, come talk to me afterwards. Thank you for the invitation. It's great to be here. It's great to be back. Things do look a little different, I think. Speaking of nothing changing, this room I think was not around or not used the last time I was talking here. So yeah. Well, the one slide summary of what we're doing is this, which many of you may have seen before. But we can look at redshift emission from hydrogen, and that can tell us a lot about the universe. But unfortunately, there are people that also like to, communicate, and that gets in the way of what we're doing. So, we'll see that for the signals we're talking about, we're going to sort of expect things around 100 megahertz. It used to be a very safe bet that everybody had a 100 megahertz receiver. That's slightly less true now, but if your favorite radio station, so that number associated with it, that's the broadcast frequency megahertz. So this is a big problem. If we're looking for sub-Kelvin signals from the early universe, if you've got a 10 to the 12 Kelvin radio transmitter next door, right, you're just not going to see it. So I will sort of, here's the rough history of the universe. This is it's actually Cynthia's plot in the back there, to co-moving volume scale appropriate. So we've got the CMB, dark ages, before there's any stars, then cosmic dawn, when stars light up, ionization, structures grow, and eventually sort of redshifted diffuse, dark energy takes over. And for almost all of this, we can in principle use hydrogen to probe the volume of what's going on. So it's great because hydrogen emits at 1.4 gigahertz. And so by tuning the receiver you look at the universe with, you can very easily look at different redshifts. So I'll talk a little bit more about this in the next slide, but the mission comes from the proton and electron being spin aligned versus anti-aligned. When they flip, there's a slight energy difference, and that's what gives us our 21 centimeter radiation. So we've got experiments like CORD and HIRAX that we're also working on that are going to be looking for dark energy signatures at lower redshifts. So I will not talk about those today. And then out looking for cosmic dawn, we have experiments working on like PRISM and MIST. So this is where edges in Ceres 3 we're observing too. And then the real long-term, the dream for cosmology is to map out the dark ages, because that is the place where the most number of linear modes exists in the universe by orders of magnitude, because the denominator scale is very small. So if we can get out there and map the hydrogen, we have actually, this is work from Matthias, I think some of the first estimates. You have 1 million modes in the CMB, and think about all we've learned from that. You have, in principle, something like 10 to the 15 modes you can measure in the dark ages. So it's a trove of information if we can get there. We're not going to get there anytime soon, but we're gonna, we're trying to start looking, at least seeing our enemies out there. So really briefly, the Wojthausen field effect. I'm gonna start talking about the cosmic dawn stuff. And the physical effect that's right here is Wojthausen field. So we measure the spin temperature of hydrogen. We measure the ratio of spin up, spin aligned, spin anti-aligned hydrogen. So that's what we actually see. But it's a very tiny amount of energy. So it kind of gets knocked around and evolves in strange ways. So in cosmic dawn, what happens is let's picture a hydrogen atom sitting alone in space. So it's sitting in its ground state. The ground state lifetime, or the lifetime of the spin excited state is like 10 million years. So basically, it's just going to sit there and not do anything. And then a Lyman alpha photon comes along, and it seconds it. And the hydrogen goes to the n equals 2 state, and then nanoseconds later decays back down to n equals 1. and sort of randomly picks the aligned versus anti-aligned state. So if I have a hydrogen atom sitting out in space and I have mostly Lyman alpha photons, so I need a slightly higher energy Lyman alpha photon to excite the hydrogen atom if it's in the ground state versus the spin excited state. So if I have something sitting in the ground state and I've got mostly low energy Lyman alpha photons, right? This thing in the ground state can't absorb. It's not quite enough energy to boost it up. But something in the excited state can pick up, can absorb a photon. So if I have low energy Lyman alpha photons, my atom, if it's unexcited, it just sits there. If it's excited, if it's in the excited ground state, it absorbs a photon, spits it back down, might go to the excited state, might go to the ground state. But of course, if it goes to the excited state, it can absorb a photon again. And the same process happens. And eventually I turn all of my spin excited hydrogen atoms to ground state. So I can cool the spin temperature. I can make all the hydrogen unexcited by pumping in Lyman alpha photons with low energies. Similarly, if I pump them in with high energies, I can preferentially turn the ground state into spin excited state. So when I when I have hydrogen out there and I pump in Lyman alpha photons, what happens is that the spin temperature, which is what we're going to observe, gets very quickly follows the shape of the Lyman alpha profile that these atoms do. And that can come from Lyman alpha emission, but it can also come from things like X-ray emission. Of course, you can probably guess that because the Lyman alpha absorption cross-section is so high, when I have a photon, it gets absorbed and emitted, typically hundreds of times before it eventually, wanders out and gets redshifted out of the Lyman alpha band. And so the net effect is that when I add in Lyman alpha photons, what they do first is not heat the gas. They couple the spin temperature back to the kinetic temperature of whatever is emitting the Lyman alpha photons. So I'm not going to heat the gas. I'm going to follow the kinetic temperature of the gas. That's the Wojtausen field effect. And that's what really is driving this plot now, which is the average sky brightness of due to 21 centimeter hydrogen as a function of redshift in the early universe. And there's many temperatures going on here. And the fact that the excited state lives for 10 million years plays a very important role. So what happens? Well, I have a Big Bang, we have a CMB, and as things expand, they cool. Matter cools faster than radiation because you have a gamma of 5/3 for matter and a gamma of 4/3 for radiation. So as I expand, the dark matter is never coupled to anything. So it just starts out cooling right away. So after the Big Bang, the dark matter cools. Initially, the gas stays very thermally coupled to the radiation, right? So that's what happens all the way up to the CMB. And so the gas temperature stays locked to the background temperature because I have a bunch of gas and a black body, and it stays coupled. Sort of not right at CMBs, maybe redshift of 100. Eventually, those temperatures decouple, and now the gas starts to cool as the universe expands relative to the CMB. So CMB is dropping, the gas is dropping faster, and the dark matter has dropped even faster. And so if I look at the average brightness, this is what you're seeing here is initially the spin temperature is coupled to the kinetic temperature of the gas because the atoms are colliding. And so if I have lots of atomic collisions, then things will go to thermal equilibrium. And so I get a spin temperature equal to the gas temperature. But eventually that collision rate drops. And so the spin temperature is going to start to go back towards the CMB temperature, but it takes a long time because it takes 10 million years to decay. So it also takes 10 million years to absorb. So over, tens of billions of years, the spin temperature goes back up, and then the first starts to turn on. And they put out Lyman alpha photons, and because of the Wojtausen field effect, what happens first is not that the gas gets hot, but the spin temperature snaps back to the kinetic temperature, which remember has been cooling faster than the photon temperature. And so now I see not a brightness, but a dip in the average brightness of the sky.
So
Eventually.
equal amount of absorption as well as stimulated emission.
So there is more absorption than emission. when the temperature drops, right? Because it's a,
Okay,
the CMB is a backlight. Then I've got this cold gas that's colder than the CMB in front of it. So now it absorbs photons, but it can only absorb photons at the 20 centimeter line at that redshift. And so if the gas is colder than CMB at a given redshift, it absorbs.
but if it absorbs, then why is the brightness temperature going down if it absorbs more than it emits?
Because that's what happens. I've taken away photon, so I get a negative temperature. So the
Okay.
20 centimeter photons are getting absorbed as they come through because the temperature is
So
low.
it's the temperature of the 21 centimeter photons.
Yeah, just the 20 centimeter photons, right? Because this is what we see. What we can measure is the spin temperature, which is not the kinetic temperature. And so this drops, but eventually when I heat, well, eventually as you pump energy into something, things heat up. And so eventually you get a bump from reionization, and then reionization sort of starts here. And once I ionize the hydrogen, all this all goes away because I no longer have any 21 centimeter photons happening. I need people to do that. And
Sorry, why after first start before, it go back to couple to the kinetic temperature, okay?
yeah, because so the white doesn't feel
Cross section change, or?
which cross section.
No, I don't know, I'm asking.
Yeah, okay,
Why
so-
originally is, you said it's coupled, so the original coupled to the CMB and then
So
it directly
it's originally coupled to the kinetic temperature,
Right,
and then collisions drop, so it becomes coupled to the CMB.
right, but then they start to go,
But then once I have even a few Lyman alpha photons, right, what happens first is that the spin temperature becomes coupled to the kinetic temperature again, because the Weyerhaeusen field effect is so efficient at getting the spin temperature to go back to the kinetic temperature. So, I can hit my Lyman alpha photons say every million years, but it takes 10 million years for the CMB to get. So this is entirely because of Lyman alpha. So if I had earlier Lyman alpha photons, this temperature would just follow the kinetic temperature all the way.
okay.
But it, well, we're not totally sure what's happening, but we think it doesn't do that.
Okay.
And so eventually it goes away. And so this is the signal we're gonna look for. And there's a very sort of robust prediction here, which is this brightness temperature, right? Because this is going back to the kinetic temperature of the gas, and this is just adiabatically expanding, right? This is no more complicated than your refrigerator. It is very difficult to make this colder than the gas kinetic temperature. It's easy to make this go away, but it is really, really, really hard to make this dip deeper than the kinetic temperature of the gas at that time. So, we have a very robust upper limit on how deep that dip can be.
And the shape and the location where this happens will have something to do with this like interplay between when
Yeah.
you turn on the first star.
So- Thank you for the question, because my next slide is, here's now a set of models, so 200 reasonable models drawn from people's guesses of what star formation in X-ray might look like. Each of these curves is a different model. So you can see there's this overall bounding thing, right? This is the gas kinetic temperature. This is why nothing drops below there. Things that are blue have relatively more Lyman alpha production, relatively more star formation. Things that are orange, yellow, red have relatively more sort of early black hole production, X-rays coming out from black holes. And you can see stars, more Lyman alpha means I get a deeper dip because I'm not heating the gas very quickly. I'm getting to the kinetic temperature quickly. As I add more X-ray photons, I don't get as much of a dip because I'm heating more, and I'm not seeing the kinetic temperature, the X-ray temperature, the X-ray absorption temperature, emission region temperature matters more. And I also get more heating because I'm putting more energy in quickly. So I can make this go away. This frequency tells you the redshift at which stars turn on, right? That's very clear, right? Because I don't get a dip until I have photons, and those photons are, we know they're 21 centimeters whenever it happens. So I can just read off in this frequency the redshift where cosmic dawn happens. That's very, very stable. And then, yes, the details depend on what these first luminous objects were, whether they're stars, whether they were black holes. And so that's one of the reasons we'd really like to be able to do this, because we don't need to look at bright objects or lens rare objects. This tells us just from the shape of this, a lot about what the first luminous objects were and when they turned up. So it's great if we can get there. Talk about all this. Oh, and yeah, so this should be really easy. So if you work through the math, right, we're looking for the average brightness. We only need one antenna for this. We're not trying to image anything. These are easy frequencies to work at. As I said, everybody's got a 100 megahertz receiver in their car. And if you work through the numbers, you know, this signal is pretty bright. These are not units cosmologists who look at radiation fields are really used to most of the time. This is, you know, tenths of a Kelvin that we expect. So the sort of the canonical maximum depth you're going to see is about a quarter of a Kelvin. And if you work through the numbers from the radiometer equation, right, this should take a couple hours. Piece of cake, right? What could go wrong? Well, no, it's not that easy. Or we have measured this a long time ago. Total power measurements are really hard, right? There's a reason that FIRES had to go to space and be very carefully calibrated, and we don't do that from the ground. And like there hasn't been a measurement to supplant that in 30 years. And systematic errors really hard. Like you don't really get to switch your data because any constant systematic error looks just like the signal you're looking for. So it's really hard. You have to really understand. And the sky signal is so much brighter than what we're looking for. So just to sort of illustrate this, here's our little cosmologist trying to peek through peek out of the sky and see the birth of the universe, see the birth of the first stars. So here's our signal that we're looking for. Here's our nice little cosmic dawn photons. Well, then we go through the galaxy and get a lot brighter photons. So this is, you know, 10,000 times brighter roughly. Then we have to come through the Earth's atmosphere. There's an ionosphere, which can affect things. It can bend, absorb. And now our signal is a little bit more corrupted. And then we have, you know, Selena Gomez broadcasting, and we have to handle that. And then that has to come in our instrument, but, you know, our instrument may actually radiate itself because anything that absorbs emits too. And it's, you know, you have to be very, very careful that you don't go to a really quiet place and just end up observing the RF signature of your electronics. But then when you're trying to move 4 grams of a part in 1,000, your instrument, you better really understand your instrument because these like are made out of physical metal panels and maybe they're like not exactly cut the way you thought they were. Maybe there's like some dirt that's affecting the impedance match between your antenna. It's like it gets very complicated. And of course, we have friends and that we have to deal with. So over a drink, you should ask Cynthia about some of her mouse proofing cables. She's learned a lot of psychology of mice and what deters them from chewing on your cables, but it's a real problem, you know. You go out and put up an instrument and then a mouse chews through your cable. That's it. So more quantitatively, here's sort of typically what we're looking for. Now that's the same plot, but now on the units you're actually going to see given the brightness of the sky. So you can see we went up from tenths of a Kelvin to 10,000, you know, 10,000 Kelvin. Here's what the Milky Way looks like typically, but of course it's not the same in every direction. So you can get a spread. We have to be able to get rid of all of this to see the depth. Then we have our radio station. So FM is the worst. Then we have our real instrument, but now we have our real physical instrument. So maybe we have some emission and maybe we have some ripples from imperfect cables, which may be from critters, but also there's always reflections whenever you build an RF system. So there's always some sort of ripple. So this is what we're actually going to see. And we're going to try and go from this back to that. So it's become more popular recently, especially since edges came out. But here's a sort of brief. I'm not going to talk about all of these, but I'll talk about a couple that have put out results. So the first big one was edges. So this is a blade dipole in Western Australia, and they came out now about 5 years ago with a detection of a thing they said was on the sky. They're very careful to say we think we see a dip on the sky in the average brightness, and not explicitly say that this is cosmic dawn. Of course, that's what they were looking for and hope it is. But the thing that immediately jumps out, if you look at the other plots before, is that the depth that they see is half a Kelvin. So that's about twice as deep as the maximum depth you can have from just for standard physics. And as I said, right, it's really easy to make the dip go away. But if there's something larger than a quarter Kelvin, then there's some weird physics going on. So this generated lots of excitement, and is still, people are still thinking very carefully about that. So that's what it looks like. If you go to like workshops with people who spend the field, half of what we talk about is this stuff out here. So this is the ground plane, and you'll see this like edge, got little diagonals cut into it, and that's to try and impedance match because it's very easy. You've got this antenna, it's sitting on ground, and that makes the ground part of your antenna. And so the point of this is to try and make a perfectly conducting plane so that you know what's underneath you. But there are always reflections. So if you make a small ground plane, then you'll get a ripple in frequency, which is what you're trying to search for, just based off of EM waves like going through this ground plane, reflecting off the edge and coming back. So like these cuts are to try and make that impedance change smoother to cut down on reflections. But yeah, if you have dinner with Alan Rogers, he will just fantasize about building a kilometer wide ground span, and that's what gets him excited. So there's lots of small things can make big differences. So this is what they actually saw, and it's important to keep this in mind when you go off and look at models and compare that to try and compare different experiments. So here's their nice observed spectrum, nice parallel looking thing. And then they fit a parallel model, subtracted off. I think this is a 7-term model, so there's been a lot of filtering. And this is the residual that they got, right? So this is really the plot that is their result. So if I subtract off a 7-term polynomial times parallel, with some other things in there, this is what you get. And these residuals look larger than the noise. So they came up with an empirical model, which is this flattened Gaussian that looks sort of like their dip. And when you put that in, include that as a fit, then you get residuals. And if you add just the Gaussian part back in, then this is what you get. But remember, when you've done this, you basically put a very strong high pass filter on whatever model you put in. So the flattened Gaussian is consistent with the data, but any model that gives the same high pass signal would also be consistent with their data. So this is not driven by physics. This is what our thing looks like. Seems to be a good enough fit, but you have to be very careful. So if it's right, it's really hard to explain. So right, we're twice as deep, and the signal looks like the spin temperature times the difference in spin temperature between the background temperature times the background brightness temperature. So if I want to make a really deep dip, either I have to raise the background brightness or I have to drop the spin temperature. And that's basically what all the models that try to explain edges are doing. So somebody here worked on really large dark matter. So what's happening there is, remember, the dark matter is expanding faster. So if I can somehow couple the spin temperature to the dark matter temperature, then I can make a deeper dip. Or maybe I've got some sorts of radio background, so the CMB temperature is a lot brighter back in the early universe at low frequencies. And maybe well, not CMB, but there's some brighter background, and then that would give me a deeper dip. But you have to either make the background brighter or the spin temperature lower. And both of those are hard to do with standard physics. And Jordan Baraka, who was formerly at McGill but has moved on, has written a lot of nice papers about other challenging aspects of this too. So if you say you think this is flattened Gaussian, that we take the model seriously, then it's actually even hard to explain that ignoring the depth based, with getting the shape right with sort of standard galaxy star formation is hard also. Yeah, there's something. Yeah, so right, I get T radiation over T spin, and I get so I got to make TR bigger, TS smaller. And slightly more speculative, but there are hints that there's something strange going on in the early universe, so young universe. So this is a plot from Hooper et al. Last year showing the basically SDSS data showing the co-moving mass density of black holes of varying masses as a function of redshift. So, you'd expect that as universe evolves, you get more and more large things to look at. And indeed, that's true for low mass supermassive black holes. As I go to lower redshift, I get more of these 10 to the 7, 10 to the 8 solar mass things, more of the 10 to the 8, 10 to the 9 ones. But as you start to go to the very high masses, it kind of flattens out. So, most of the mass on the 10 to the, a lot of the mass in the 10 to the 10 to the 9 to 10 to the 10 black holes was in place fairly early on. And there's almost no growth at all in the really biggest black holes. So these things, sorry.
Finish your sentence.
Yeah, so these things seem to be forming a lot earlier. And if I can make black holes that put out a lot of, say synchrotron radiation early, so I have to do that before the stars turn on, because I have to raise the background temperature when the absorption is happening. So maybe something is going on that's putting out radiation back then. I don't know if Edges is right or Edges has a systematic. It's really hard to say that.
So if you take that function that you add, the single dip function, and you allow it to have something that goes up, like, so you showed that plot earlier with all the different colors, and you said you have some, right? Yeah, so if you modify the top right plot here to allow it to go up, to have 2 different features, so that it could, for example, more match some of the more yellow lines on one of those earlier that you said has more.
Yeah, no, that's a great point. I think, people have done this, and even doing that, it's still very hard to fit. People have also said, hey, I think this may not be from the sky at all. What if I have resonances between the antenna and the ground? And if you look at the, if this sort of, this is 20, 30 megahertz, or, some number of megahertz, and that gives you like a size of a feature that you might expect is doing reflecting if you want to put a ripple. And that size is like not that far off of their ground plane size. And there've been papers about, what about some other standing waves you can get right, this wavelength is, a few meters, so a quarter wavelength is roughly the height of the petals. There have been very few papers about why this might be wrong experimentally, but it's completely possible. And there's also this, which is the Arcade 2 measurement, which has been around for a decade, and we all just kind of as a community decided to ignore it because nobody knows how to explain it. But they did an average brightness from a balloon, sort of like redoing FIRAS, but at lower frequencies. And they see unexplained excess emission at low frequencies. There is plenty of signal here if this is coming from cosmic dawn to explain what's going on. I'm not saying it is, but it doesn't, if you extrapolate that to lower frequencies, right? As long as this happened early enough, maybe there is some strange background. I don't know. It's really hard to do this in an actual model. People have tried a lot and can't actually really do this with simulations, but just qualitatively, that this could be happening. And then, of course, we're working to reproduce this, but there's also been results, I guess, a couple of years ago now, from an Indian experiment, CERES-3, and they floated on a. Remember, I said you talk about this with the hardcore people. We all care about the ground planes. So their scheme was to go float their antenna out in the middle of the lake and use the lake as a ground screen. They did have issues with the crocodile once or something.
Yeah, the crocodiles knocked over the antenna.
So it's a kind of a wild world in this field. So we're trying to get away from people, so you're away from people. And they said, okay, we'll take our data, we'll fit the Edges profile to it, and they don't see anything, but barely. So it's I think less than 90% statistically significant disagreement once you include the errors on both CERES-3 and Edges. So they're very consistent with no cosmic dawn signal, but they're not very inconsistent with the edges signal either. And then this is, again, one of the, this really highlights why we go to these strange places I'm going to talk about next. So Ceres 3 is in India. You may have noticed that there are lots of Indians in the world. So it fits the population now. So it's very difficult to go somewhere where there's just no emission. So they have to cut off at 85 megahertz because FM kills them above that. So they just can't look here, and that's because they're trying to observe from India. And even if you go away from people, one of the big challenges is that there's always little tiny meteorites coming in. And so you've seen meteorite trails. You photograph meteorite trails. So that's ionized, as they come in, they ionize, you're seeing the ionized gas. Well, ionized gas is a great reflector of radio waves, so you can pick up FM stations off of meteor trails. So even if you don't see FM directly, even if you're within thousands of kilometers, it can be a problem because all those meteorites will reflect FM into your signal. So they have to cut off at 85 megahertz, which means they don't, edges got to see the signal go back up over here, but they don't get to see that. It is almost certainly true that if you put in the edges model, that there's a mild conflict, but not a strong one right now, but a mild conflict between Ceres 3 and them. But I can cook up lots of different shapes that look very similar, but look very different once you filter them. So I think you could have it is entirely possible that everything everybody said is correct, and you can make models, I think, without too much trouble that would fit both edges and Ceres when you actually go through the full foreground model. So, I think a lot of people want to say, oh, okay, after Ceres, we can ignore edges. I don't think that's the case. I mean, it may still turn out to be that cosmology is nice and boring. 90% of the time that's true, but, my advisor said he was going to leave the field of dark energy turned out to be a thing, and that, well, he didn't. So that brings us to the first experiment of ours we're going to talk about. So this is probing radio intensity at high Z for Marion. And we, to try and get away from people, we've gone to some of the most rural places on the earth. So I actually learned about this island by reading an airline in-flight magazine. So they were talking about how they had a new science station. I was like, hey, I can think of things to do when you're got a new station that's far away from people. So here's where it is. At South Africa. The island is here. It's about 2,000 kilometers away from the mainland, and is, I think, the most radio quiet place we have ever seen or found or heard of on the earth. So it's really gorgeously clean. So we proposed, I think, in 2014, 2015. Fortunately went through. So we started our first science engineering test runs 2016. And then operated between 2017 to up till last year. So it's very challenging to work out there, but it is the cleanest RFI site that we've ever seen. So here's some of our intrepid people. We have to put our telescope several kilometers from the base because you don't want to go 2,000 kilometers and then just see everybody's laptop. So they have to hike out several kilometers behind a hill. You can ask Cynthia. I've never been. You can ask Cynthia about stories, hiking stories. It's the base mostly there to support wildlife and geology type things. So I think a third of the world's wandering albatrosses nest on this island. It's full of penguins and seals. So this was Mohan's picture, right?
Yeah.
Yeah. So it's very easy to look like a National Geographic person when you go out there because it's just such a stunning sight. You can see all the only way to communicate reliably was via WhatsApp. We couldn't even send emails like they'd sometimes make it through. So you'll see we have a WhatsApp list of all the critters that they saw. But here's where we go. So here's raw data off the telescope. No processing. So remember I said that cables always reflect, so you can see these reflections here. But what you don't see at all is any FM emission, right? So if you go to a radio astronomer and say, hey, this is the total power my instrument measured, they'll think you're lying most of the time. Because can't get away from FM from most places on Earth. And this bump right here, so this is the brightness temperature. This is the galaxy rising and setting. And so as the galactic center comes up and goes overhead, we see brighter signals, and as it sets, we see fainter ones. That's the data, beautifully clean. And we're in the process of analyzing it. And then we've also got another one started. So this was with Raul Monsalve, who was sort of the lead postdoc on EDGES. And this is his, well, now that I've done one, I'm gonna redo it and do things differently with the experience of EDGES in hindsight. So what you notice here is that there is no ground plane. And the idea is, well, again, you want to try making this measurement as many ways as possible because we want to see the different measurements give consistent results. Because that's a really powerful hint that we're not seeing systematics. So rather than worrying about reflections off the ground plane, what if we just don't have it there? So you use a little bit of sensitivity, but then you have to model the ground underneath it. Because now the ground is part of your antenna. So Cynthia's got students that are, sticking probes in dirt and using ground penetrating radar to try and map out the impedance and conductance of the dirt underneath the antenna. So if you want experiment details, there's the paper. It's pretty hardware. And here's where we've gotten. So one of the reasons we were really excited about moving to McGill 5 years ago is that they have a research station on Axel Heiberg, which is the world's 6th largest uninhabited island, and is it's 79 degrees north. So it's far away from people too, and that's sort of the main missed science site. But we've also got a test site out here. This is about a 12-hour drive from Montreal. There's still FM, but the background is very low, and so we can, relative to most places, you can get. So the background's very low. So we go out there, and there's a mostly a hotel, but they call themselves a research station. So they're very supportive of people who want to come and do research. And Rail's in a couple runs from Death Valley and Deep Springs. We're driving distance from Berkeley. So why do we go to our high Arctic site? So McGill Arctic Research Station or Mars. So here's what the RFI looks like from Mars. So this is actually a paper led by an undergrad with us who's now at Stanford. And we were very aggressive in labeling things RFI because we really wanted to dig down to the noise. And you see there's basically no persistent RFI that we see in the FM band up there. So it's, it's not quite as clean as Marianne. Occasionally flashes come through, but it's very, very good. And much, much easier to get to.
Just curious.
Yeah.
So that looked like it was relatively close to Tule.
It depends on relatively. So we actually do see the navigation beacon from Chile.
Yeah, so like, do you have?
That's out of band.
Yeah, so do you have agreements with them to not broadcast that?
No, nobody cares about us.
Okay.
But it's the Chile beacon. So the thing we see is the Chile navigational beacon at the airport, and it's like a very narrow band, right? So it's 112. We lose a tiny bit from that, but it's not like this broad losing the whole FM 10 megahertz right at the peak of your signal. So that's way down our list of concerns. So we didn't see things like that from Marion. We do see things like that from Mars, but I will show you though. It's just not going to be a big concern. So here's some missed data. So here's some Deep Springs and Death Valley. So you can see like something happened over here. Somebody did a burst or something. Maybe that was a car driving by. I don't know. These things happen. Well, no, that'd have been longer than a car. And here, this vertical stuff, right? So this is frequency. This vertical stuff is the persistent FM, right? So remember, this now is in there's no color scale, right? But oh no, this color scale, right? So this is hundreds or thousands of Kelvin, right? We're looking for something faint, so you can't use this from here. Here is now the same plot, but from Mars. So you can see that stuff is all gone. So it's a really nice place. Plenty clean enough to do the cosmic dawn experiment. So then just in plot form instead of graph form, here's preliminary spectra. So here you can see from Deep Springs, you see all the RFI, Death Valley, even more RFI, and then here's the same spectrum from Mars. Right. So it's very nice. And here's, this is the 2022 run. This is now fourth order fit, so we're trying to like not look at, we know this is not enough orders to actually fit the foregrounds. But, excuse me. For checking how this is behaving, this is now every hour over several days, what the spectrum looks like after that removal. And you can see that it's beautifully consistent. So the instrument has lots of sensitivity, and very consistent day to day and even hour to hour as the LST changes. So we're busy analyzing this and PRISM data, and stay tuned. It's challenging.
So when you say 4,000 point nominal, that's within this range or using wider range?
I think it's using the 50 to 100.
Okay. And the signal is supposed to be around 70 to 80?
Yeah, ish. I mean, it depends on when you think the first star is turned on,
Okay.
but that's, you know, 70, 80, 90 is sort of the typical guess. You know, maybe GWST is pushing that a little bit lower. The edge of signal was centered at 78.
Okay.
But that was surprisingly low. People, you know, the expectation was going to be higher. But we don't really know where it's going to be. That's why we're doing that. So, you know, these data are looking great. Few glamour shots, because, you know, I'm guessing most of you have not deployed instruments to the Arctic. So if they're on a Twin Otter, which is that plane right there, that's actually the planes, like if you have to do anything like unexpected at the South Pole, those are also the planes that you use. Ken Borg Air is like legendary and all of these remote things. And this is a Ken Borg plane. So fortunately, we have a lot of glaciologists that worked up there that have a lot of experience that have been really valuable for like, you know, how do you like put your stuff up and not have it die under the snow. One of the reasons for going earlier in the season is because it's a lot easier to run on a snowmobile than on foot. So here's our intrepid team snowmobiling all of the hardware, because again, you want to be away from the base. So they took it several kilometers away. Classic Arctic scene. And here is Burgle and Ian, very happy after having set up NIST. So, and here is the most recent, a chunk from the most recent season data. So we've got 2 years of, you know, two observing runs of the data in the can. We'll be going back in this April. Right. So that's the basic story for the global signal. There's a lot of information in the signal. If we can measure it, it's really hard. Indications of something should be happening, but we need lots of people to make the same measurement before we can really have confidence that any measurement is correct. So in the last little bit, I'm going to talk about Albatross, which is an even lower frequency experiment. And so again, the long-term goal, you know, the pipe dream of all cosmologists, whether they realize it or not yet, is to go off and measure the dark ages. But the universe, the Milky Way gets even more complicated low frequencies, and interference gets even harder to handle at low frequencies. So BBC World Service, have you ever listened to that on shortwave? So shortwave goes a long ways, which makes it really hard. So the ultimate dream is to image the fluctuations, but we actually don't have any decent maps of the low frequency, you know, below 10 megahertz sky right now. So Grote-Reber, the state of the art is Grote-Reber back in like the 60s, 70s from Tasmania, managed to get like a 5-degree resolution map of the sky. It's about 2 fists worth resolution. So we don't really know what's happening there. And the reason is, you know, as hard as the ionosphere tends to block this. So you want to go somewhere away from interference and with low ionosphere if you can manage. At higher frequencies, the maps start to get better. But, you know, this low frequency, you know, especially below 10 megahertz is basically almost completely unexplored. So if we're going to these really remote places with really low interference, let's see what we can do there. So there's a lot of stuff you can do, even without sensitivity to see the dark ages, which again, like you need 25 square kilometers. We're not doing that anytime soon. But there's lots of other fun stuff. So actually one of the things my PhD student is really excited about is H1 absorption. So the sky background is millions of Kelvin. But H1 regions are 10,000 Kelvin, and at a few megahertz, they become optically thick. So you don't really see them at higher radio frequencies or see them very brightly. At these frequencies, at albatross frequencies, they should be, 5 million Kelvin holes in the sky. By looking at how much gets emitted between you and them, you can say something about distances. There's all sorts of really fun things you can do. Basically, because the galaxy at very low frequencies is also becoming optically thick. And so you can probe 3D structure by looking at how that absorption turns on as a function of frequency. There's lots of fun stuff you can do. I think we won't have the sensitivity in the first instance, but the brightest radio source in the solar system is Jupiter at a few megahertz. So this may actually be in a good way to look for planets with Jovian magnetic flares. So it's just a very different world down there. So we'd like to, to get started looking at it. So this is our thing. If you want decent resolution, you need long baselines, especially if you're looking at 10 megahertz, the wavelength is 30 meters. And if you want to, see degree, you need 50 wavelengths, and that means you need, several kilometer long baselines. We're not going to run 5-kilometer cables in the Arctic. Even if we wanted to, the critters would disagree with us. So what we do instead, normally with a radio telescope, if you're going to make an interferometer, normally what you do is you pump in the electric fields from 2 telescopes, and you have a correlator in the middle that multiplies those and tells you what the cross correlation is. Because we can't hook things up directly, we can't do that. So what we do instead is that we have every antenna operate autonomously, and it just writes its electric field data to disk locally, and then we'll cross-correlate it offline. So we started with Marion, and then now we've tested again at our test site in Quebec and have installed things. We're installing this in stages. We've started installing up at Mars. Here's another reason why Mars is a really nice location. This is now a map of ionospheric emission. So the ionosphere blocks low frequencies pretty efficiently. So if you want to see through the ionosphere, you can do it someplace where the ion density is low. And there's two main sources of electrons in the ionosphere. One is photoionization from the sun. So UV photons come in, knock electrons off. The other is the auroras. So solar wind comes in, follows the magnetic field, hits the atmosphere, and ionizes stuff in the upper atmosphere. But because things follow the magnetic field, actually the auroras are not at the magnetic pole. They're, a couple thousand kilometers away from it. And inside, this is called the polar cap, inside the aurora region, the polar cap, especially in regions of quiet solar activity, this ionosphere density should go way down. And so a place like Mars is really nice because, the atmosphere actually gets more complicated up there, but the frequency at which it cuts off drops, especially during nice, long, multi-month-long polar winter nights. So we've actually started talking very closely with ionospheric pals of ours to try and map this out. Since we will see lots of items whether we want to or not. This is sort of a few stations where we're thinking about putting them, but we have, as of now, we have 4 stations in. This is what our synthesized beam might look like if you sort of sit at 5 megahertz and use an octave of bandwidth. So remember I said it was like 5 to 10 degrees before, now we're talking 5 to 10 arc minutes. So it's a, it's like going from Kobe to Planck in terms of resolution. If you want to ask hardware, talk hardware, we have hardware. We're using LWA antennas since they have pretty good response. It's not quite perfect at low frequencies. So we're actually former undergrad design and built front ends that she's now here. But we've had a lot of students come here. Here's our back end. Important number here, like the most important number for us is that this total system draws 45 watts. Because it turns out that powering things is very hard in the Arctic. There's no sun during the winter, so you can't use solar. And when there's no sun, it turns out there's no wind either, so we couldn't even use wind power. So we had to use fuel cells So every watt is hundreds of dollars. So we really try and keep it down. Yeah, so here's Joelle. She's now in physics. But this is she's testing our electronics engineer, Eamon Egan, designed a custom USB 2 multiplexing board, right? So we need hundreds of terabytes to record our data over the winter, and we have 45 watts to do it in. So what we have is these 16 drive enclosures, and then he built these USB multiplexers. So we can only afford the power to have one drive running at a time. And so we can switch between drives, and turns out not a lot of people want to have a quarter of a petabyte running at 10 watts, but we do. So we had to make our own solution. So yes, everything's run by Raspberry Pi. So we have a quarter of a petabyte hooked up to a Raspberry Pi on the Arctic running. The drive part is running 8 watts. So that's kind of fun. And here's our power. So since we can't use solar, we can't use wind. We use fuel cells, and this has been actually by far the hardest part. The most failure-prone part of the experiment is these commercial fuel cells. They tell us are supposed to operate autonomously, and then you say, "Well, it stopped working." They're like, "Well, autonomously, but you need a person there to hit a button if it stops." So that's been a learning experience, but we're getting there. They're methanol fuel cells, so you can put sort of 4 of these jugs. These are airplane safe, which is a big deal. If you want to carry hundreds of liters of methanol around, you can just carry them on the plane. And this is enough to last through the winter. So this is at our test site. Here's the instrument schedule. So we start in Marion. We're really going gangbusters in the Arctic now. So 2022 was our first installation. 2023. We were supposed to put more up, but we only managed to get 2. And we'll have a few more this year. Why did we only get 2? Well, there are things out of your control. If you want to haul hundreds of liters of methanol a few kilometers from your base during the summer when you can't use a snowmobile, there's helicopter support from the Polar Continental Shelf Program, which is the sort of like the Canadian equivalent of the Antarctic program in the US. So they do all the logistics support. Just before we were deploying last year, the helicopter had a bad day. So fortunately, everybody walked away from this. Helicopter was completely destroyed, but everybody walked away. Nobody was hurt. There may have been some minor injuries, but basically fine. So that put the kibosh on any deployments. These are things that are very hard to plan for. So we only got heroic efforts of our crew. We only got 2 stations up, but we still got something, which wasn't clear at all. Here's intrepid students getting things installed in the Arctic. This is one of our most fun pictures. So you install something in the Arctic. There's snow. It's not going to melt over the winter. So we had very little idea whether we just get covered in snow. So this is now the mist crew kindly checking in Albatross at the end of the winter. So this is in April. And you can see that the antenna is still above the snow. So that was good. And even more importantly, our fuel cells were still above the snow. So we're still waiting for the 2023, 2024 data. We have no way to, and we're going to start Starlink this coming summer, but until then, we have no way to speak to our things out in the Arctic because there's really no way to talk to them. So what we have so far is up to 2023. And left 2 stations. The first one made it about 3 months before so this is engineering. We just wanted to see if things would work. The first one made it about 3 months before the fuel cell died with some unknown error that the manufacturer says they don't know about, shouldn't have happened. And the other one made it all the way through the winter. So we're still happily taking data when the crew showed up in April. So we were very happy about that. So this is what some data looks like. This is actually a 2-element Pathfinder in Marion. And then, oops, well, I'll show them in a second. This is sort of what this is our 2-element Pathfinder. So this is directly correlated. But one of the challenging things of this is going to be, now that I've got all these separate stations, I need to sync them up to much less than a wavelength. So I need sub-nanosecond timing. Mazer's $1.5 million that would do this for free. Well, not for free, but would do it nicely. So instead, we're using satellites that broadcast in the band that albatross can pick up, and we're using those as calibration sources. So my student Mohan Agrawal has gotten this working, and we can actually time these separate stations just using what's in the data without having to have a fancy external clock or external calibration. Here's a picture of drives coming back with data. Oops. Oh, good. I'm sorry, slides got messed up. So here's what we saw from our stations made it all the way through the winter. So remember, what we're hoping to see is signals, we really want to see is signals below 10-ish megahertz, because that's the unexplored area. So this is the median spectra across days over the course of an entire year. So well, not almost a year, August 2022, when I left it, April 2023 is when the data were picked up. You can see, so this is all shortwave radio. So this is BBC World Service over here. You can see in the winter, the shortwave is dropping, right? So that's good. That's what we wanted to see, is that when there are fewer ions, there's going to be less bright shortwave and more of a chance of seeing through the ionosphere. This is our median spectra, but of course the sky's very bright. So even if we don't get all observing time, that's okay. So now if we take the lowest 10% spectrum power over the rest of the year, you can see this. And now you can see that we do get windows, we see stuff coming down, and there's no shortwave here. So this is very promising. Since only one antenna survived during the depths of the winter, we can't make even any interference ranges at all. But this total power measure is very encouraging that now that we have sort of 4 antennas up and running and 2 or 3 or 4 more this year, that we will actually be able to sort of start to see the universe down here. So we're
What are the units on your color bar?
dB. Arbitrary. So whatever the instrument puts out, but this is not calibrated. But yeah, 7 to 8 is a factor of 10 in power. So this is fainter, but not orders of magnitude fainter than the Cincinnati galaxy. And the very low frequency stuff saturates the color scale, so we chop out like the lowest megahertz. Yeah, so stay tuned. If you want to ask about drones, ask Cynthia. Her students were using drones to calibrate antennas. And again, thanks to all the students, postdocs, who've really done the lion's share of the work here and made this happen. So, including but not limited to everybody you see here. So it's been fun. Yeah, so we're gonna have 2 to 4 new stations this summer. So we should be able to make maps, like nice looking maps next year when that data comes back. Should be able to make preliminary maps this year, at least CPC sources. And yep, thank you for having me. You were first, and then first.
So are you worried about solar activity? Because like, isn't 2025 supposed to be really good for ham radio operators?
Yes, I mean, the initial Marion, we were hoping to get the solar minimum, the last solar minimum.
But
A little bit
still
data.
expect-
But I mean, we're gonna see, right? So again, like the average solar activity is gonna be bad, but if there's quiet periods, and because we're in the polar cap, right, a lot of that is ending up not on top of us. So I don't really know. We're gonna learn a lot. Like we've talked to atmosphere people, like, oh yeah, we really look forward to seeing what your data show, because we don't understand the atmosphere up there either. So we've actually just put a proposal to put a transmitter in Eureka that we will observe as a sort of a radar with Albatross, because that'll be in the data anyways. But we hope to keep going for several years, and hopefully by the next solar minimum, we've got a well-tuned machine. So if there are ever any really, really low times, we can just go to town.
So the spectrum you had up there from your Arctic station, so there looks like some things going on up in the 80 to 100 megahertz range. Is that all FM stations that are leaking through? Air trails and so on?
Slightly complicated. So To do the timing, the ORBCOMM, so the system can handle up 125 megahertz. So to do the timing, we need to get ORBCOMM, which is broadcasting 138 megahertz. So normally, if your system does it at 125 megahertz, you put a hard cutoff in the RF at 125. So we don't do that, so we can see ORBCOMM, so that gets aliased in. So anything over here would get reflected back over here. So we've got a filter that cuts off at 150, so everything to the left of here is definitely clear. But we can't say whether something here is FM or whether it's, you know, like the Thule broadcast thing that's been reflected back, aliased back into this band. So, I mean, we used to expect, there are FM stations like hundreds of kilometers away, and meteor scatter is a thing. So like we will get some, but it's very intermittent. It's usually clear. So there's nothing persistent. But I would be a lot more surprised if we never saw any FM than if we saw, you know, some intermittent FM. So that's not a surprise, but it's mostly not happening. So most of the time it's clear. Because, you know, when you're a long ways away, there's only a small, you know, a much smaller phase space of meteors that can reflect stations into your antenna. But good eye.
I can ask another question. So regarding the cosmic dawn, like dip analysis, how robust can you expect this to be? You know, since the signal is so unknown and you have to filter it through something.
Yeah, I mean,
it's not picking out.
that's a great question. I think any single experiment, it is unlikely anybody would believe one experiment because of all these reasons. So, and that's why it's so important that you see this multiple ways with multiple experimental designs that would have different systematics. Because now if I have 3 experiments that are totally different and I'll see the same thing, then I think you could feel a lot more confident that what we're saying is cosmic dawn and not something else. But it is very hard. And if we were the only experiment to see something, I wouldn't believe us. So I would want to see other people. And to Edge's credit, like they've been very, very consistent about this. You know, we see something that's very much not what we expect, but we really want other people to look because it's, you know, so hard to say whether this is real or systematic. Yeah.
So when the Edges result came out, there were, as you said, there were many exotic hypotheses put forward to try to explain it. One of them was that it might be some atmospheric effect, terrestrial atmosphere. So some absorption process that would take a little bit of the signal away from the synchrotron the very bright synchrotron background. So Jordi Meralda and I looked at that. It you know, it looked like you had to stretch numbers in terms of, so this would be, the mechanism would be atmospheric aerosols that are spinning. And if they have electric dipole moments, they can radiate. And of course, that means they can absorb. And the brightness temperature of that would be well below the, you know, be 250 degrees Kelvin or something, whatever the temperature in the atmosphere is, well below the much higher brightness temperature of the synchrotron background. Now, as I recall, there was nothing to rule that out at that time, but it could be ruled out by looking for correlation of the Edges signal with brightness of the sky brightness with very time-dependent variations in whatever's going on in the atmosphere. I don't know whether that's ever been done. Have they collected more data?
They do have more data. To the best of my knowledge, I don't know of anybody who's looked at this carefully. So it would be fun to chat more. There's a characteristic size of the grains that would.
Well, they'd be very small particles. So these would be, you know, tens of angstroms in size, but it's you know, we don't really know what's up there.
Yeah.
Meteors coming in ablate, they create vapor, you create dust in the very upper atmosphere. We see noctilucent clouds and so on, but there isn't a lot known about it.
I think we should talk more. I haven't thought about this. I could possibly think of if you had a sort of a higher resolution imager that you could look towards the horizon, where you'd have a larger path depth, then you see a different signal towards the horizon than.
Sure, yeah.
So you can't do that with an antenna easily, but you know, with the radar from Eureka, maybe we could work something out. I don't know. It's interesting suggestion.
Let's check.
Yeah.
Any other questions? If not, let's thank the
Thanks,
speaker
very
again. and-